Okay, did you try this question? It is there was a trap, and the trap was that the relationship between x and z is not linear in this example. So, how to tell how to tell it's not linear? Simply, you may see the slope. So when the number of trips increases from 0 to 1, the increment in z was 0 here. It does not change. So slope is 0, but when the number of trips increase from 1 to 2, the increment is 1000. So z increases by 1000 in the second increase. So that means the slope was 0 at the beginning and then goes up. So there is no, it's not linear. There is a kink. So there is a kink, which means it's not linear. So that's why it's not linear. When it is linear, so it's hard to show why it is not linear, because when it is linear, I can show you the linear function. When I write down a linear function, then that shows it's linear. But when it is not linear, then there is no linear relationship. So I cannot write down the functional form. So this is one possible way to tell the nonlinearity. So anyhow, because the relationship is not linear, uh, we cannot apply the uh, simple formula does not apply here. That means, as I said earlier, the exception, it was not an exception. So that means the expected value of the original random variable does not help. It is useless. It does not matter how many times I expect to go there. You have to recalculate everything. So put it this way. Then you have to make another table for the new random variable z. And I will calculate, the method is the same. We are doing the same method, but the other method was not working. So multiply 700.5, 700.4, and 1700.1, and you get these numbers. And if you add those numbers, you get 800, right? I I believe it's simple. When you try to exercise, when you do the homework, you may use Excel or calculator. So multiplication is not your job; it's a calculator's job. So, and I just want you to see how we get this number. We multiplied this, multiplied this, multiplied this, and we get this, right? Multiply within each row. Anyhow, in the end, we got $800. So when you buy the ticket on eBay, the expected spending becomes $800, which is greater than the expected spending based on the regular price. Regular price, well, using the regular price, the expected spending was $600. The reason is because the probability of losing $700 dominates the gain when I get the discount. So the probability of loss not using the ticket is too large. It's 50%, which is even greater than is the same as the other 50%. So in the end, we can make a decision. This is so basically, as basically the point is, we in many cases we are calculating a measure of central location to make a decision, to make a correct decision and make decisions easily. And this is a clear example. When you consider whether you buy it or not, this is a good example how to make the decision. Okay, and I will consider another tricky example. Now, there is another option. I studied very hard. I researched it very hard. how to go to Disney World, and I found an annual membership, and I need to pay $600 upfront to join the membership. But when I become a member, I can get a ticket for at a discounted price of $500. So I can buy a ticket at $500, but I have to pay $600 upfront. So then it means even if I don't go, still I have to join the annual membership now. So I have to decide whether I join the membership now or not. So $600 is paid now, even if I don't go. And then once I go there, I get the discount, member discount. So I have these numbers. So $600 is everywhere. And if I go once, I pay $500 in addition. And if I go twice, then I pay $500 twice uh, upon in addition to the membership fee. Then, given these numbers, what is the expected value of this new random variable? This new random variable is defined as the total spending if you use this membership. If you join this membership, then what is the expected spending? Do this again, try this again, and in particular, if you are confident in the algebra, then think about whether you may apply the linear relationship or not. So that's the most important point here. And second is the algebra. So try this. I will uh, now I will turn to the next page. Next page. The answer is yes. They are linear. They have a linear relationship because your spending will be $600. Once you join the membership, you already paid $600. No matter how many times you go to Disney World, and plus each trip you have to pay $500. So $500 times number of trips plus upfront membership fee. And we know that the expected number of trips was zero point 0.6. So you may simply use that. And then it's very simple. Plug zero point 0.6 into here, then you get 500 times zero point 0.6 plus 600, which is $900. So in this case, it's as simple as this. And I would not. So first, how do we know it's linear? Because you can write this way. It shows it's linear. It satisfies the linear functional form. So nothing more to prove. I already showed you I can write it this way. And then plug in. By the way, in the end, the expected spending is now $900. It's even higher than the eBay ticket. So now the decision can be made easily. It's not worth. The membership is not worth. So you may also use the uh, the the standard way, the general way of calculating probability weighted outcomes. You can do that. Multiply probability to outcome, dot dot dot, and add the three numbers. Of course, you have to get the same number. Otherwise, something is wrong. Okay, so we have studied a simple, interesting example about Disney World, and I want you to see the idea of linear relationship. Linear relationship will be used later in theory, in our theory. That's why I I empathize this example here more. So actually, textbooks may not have this type of results in the textbooks, but I think this is very important. And additional, oh, I forgot to say this. So the linear relationship, the easy result, simple formula following the linear relationship is specific to the expectation. Other measures do not satisfy this do not have those simple properties. So you may think it's natural, obvious, but it's not obvious. There are very few operators, measures that have this nice property. One of them is the mean. So that's why mean is popular and useful. So thank you for listening. I'm going to continue to the next topic. Next topic is a little bit different from this, so I will stop the video here and see you in the next video. Thank you.